partial measurements and its application to C. elegans neuronal calcium dynamics. So let's start by reading the abstract. Did everyone finish?
Yeah.
So do we have any opinions about this abstract? It is clear, and I think the gap is also clear. Usually it's indicated by however. So here, the gap is that however, it is unknown how the performance of link inference techniques on such data sets depend on the limitations of data acquisition. But personally, I think it's not really unknown. Basically, if your data is not good, the link inference technique will not perform well, right? So I think that's common knowledge in link inference techniques. But anyway, let's take a look at the approaches they used in this paper. So as mentioned in the abstract, the performance of network inference methods, it is dependent on the quality of the data. So for example, we are taking a look at two variables x and y, and the ground truth is that both x and y affect each other. Usually, the process of link inference methods is that from the time series data, we perform inference, and the inference method will give a criteria for some type of score that is resulting from the inference method. After that, the score computation is performed, and then from the scores that we get, basing on the criteria, we get the final results. So for example, in the first case, we have very finely sampled data. So this is a very beautiful data. The data is very smooth. And usually, after performing inference in this kind of data, it will give us very good scores that will pass the criteria of the inference method so that the final result will be correct. But in other cases, such as cases where the sampling rate is very low, usually some of the links will not pass the criteria of the inference method, such as in the second case, where only one of the actual links is detected. And finally, for very noisy and very sparse data, sometimes the actual data doesn't look at all similar with the actual underlying dynamics. So that sometimes we don't even detect any of the actual relationships. So in this paper, as mentioned in the abstract, they tested three different methods for inference. The first one is the very common inference method called Granger causality. And the basic idea for the Granger causality is that they construct two models describing the dynamics of y. The first model is just a linear function of lag versions of just y, and the second equation is just the linear function of lag versions of y plus the lag versions of x. So what they do in Granger causality is just compare the two models, and if the second one improves the performance of the first one, then there is a connection between X and Y. That is the very simple idea behind Granger causality. And the second method is transfer entropy. This was discussed by Eugene about maybe 2 weeks ago. And transfer entropy is just, the idea is just based on the shared information between the variables in the system. And finally, they assessed a type of machine learning method to detect the inference between the variables in the data. And after testing all these inference link techniques, they also applied something that we call surrogate data testing. So later on, I will show you how this is performed. But since they use a lot of different methods, we will only focus on this machine learning approach and the surrogate data testing. Any questions so far? So this is the basic foundation of the machine learning method that they used. Their assumption is that the dynamic of the network is governed by a general differential equation. So for example, we have two nodes, x1 and x2, and this is the general equation for their dynamics. Then we can say that there is a causal link from x2 to x1 only if f1 is a function of x2. So basically, if we take the derivative of f1 with respect to x2, we expect that the value is non-zero. And at the same time, if there is no causal link from x2 to x1, then f1 is not a function of x2. So that the partial derivative is expected to be equal to 0. So it's very easy, the basic foundation. And in general, for n nodes, a link exists from xj to xi only if the partial derivative of fi with respect to xj is not equal to 0. So actually, if we know the form of the function fi, then it is very easy to tell if there is a link between the two nodes. However, of course, we only have the time series data and the function fi is unknown. But even if fi is unknown, we can estimate its partial derivatives. So take note that we are dealing with time series data here. So our data looks like this. It's just the measurements of our variables at specific time points. And then we can estimate the next time step using this first order Euler approximation. And we simply take the derivative with respect to xj at some time point. And here the delta ij is just 1 if I is equal to j, and it's 0 if we're not looking at the same nodes. So simply, if we want to test the non-self-regulation, so if we are looking at two different nodes, we are just taking a look at this equation. So this means that if the underlying function, if its derivative with respect to xj is very close to 0, then this thing will also be very close to 0. So instead of looking for the form of fi, we can estimate this value instead. Clear? So first, we don't estimate the partial derivatives directly, but we estimate the next time step, the future next time step of our current values of our variables using what we call a reservoir computer. So this is just a special case of a machine learning model where we have an input layer, a hidden layer, and an output layer. Here our input is just chi, but this is just a concatenated values of all our variables at time n delta t. And the output that we expect from this reservoir computer is the next time step prediction for each of the variables. Okay, so this is how, now I will start describing how reservoir computing works. The first step is to initialize our reservoir. So for example, we have some D number of reservoir nodes within this hidden layer. Usually this is a very large number of nodes, and in this particular study, they considered about 3,000 reservoir nodes. And after initializing the reservoir nodes, we also initialize what we call an adjacency matrix H, which is D by D. And this H will describe how each of the reservoir nodes affect each other. And after initializing the reservoir, the next step is to feed our input or the current states of our time series data into the reservoir using what we call an input matrix W in. And this is the rule for the updating of the nodal states. So the role of the input matrix W in here is just to project our low dimensional input time series into the high dimensional reservoir computer. And this is the update rule. Here, sigma here is our activation function, which will introduce the nonlinearities in the relationships. And in this particular study, they use the hyperbolic tangent function, which is a usual activation function. And finally, the next step is just to predict the future state. And simply, we can simply predict the future states by training the output layer via a very simple linear regression. So here we get the current state of the reservoir nodes, and we use that to estimate the output matrix W out. And this will be the estimate of our future nodes. And we perform this training by minimizing this cost function. So this is the estimate to our future state. We want to make it as close as possible to the actual value by minimizing this. And this term is just a regularization so that we can avoid overfitting. Okay, but now so far we only estimated the future time step of our time series. But what we need is the estimation of the partial derivatives. So first, in order for us to estimate that, let's recall that these are the equations for the evolution of the nodal states and the estimation of the future states. We want an equation where where we know all the values. So we want to eliminate the terms that involve the reservoir nodes. So basically here, what we do with the left-hand side of this equation is that we replace the r and delta t by from this equation, so that the left-hand side will become this one, and then similarly on the right-hand side, the r of n minus 1 delta t will be replaced by using this equation of the future states. And finally, we just multiply both sides by W out so that we have this equation for the next time step. And then, as you can expect from here, we can estimate the partial derivatives with respect to a different node. So take note that these are all, this is a vector, and these are composed of vectors and matrices. So chi of n plus 1 delta t contains of x1, x2, and so on. So if we estimate the partial derivatives, we just make it component-wise. So actually, this looks very complicated, but this is just chain rule for each of the components. And as you can observe here, all the quantities on the right-hand side, we know them. So the Wn, this is just the input matrix. We initialize this matrix. Same with the H matrix. And the W out matrix is just the one that we obtained from training the reservoir computer. And chi and delta t, this is just the current state, and we also know this value.
What is the sigma prime?
Sigma prime, oh, this is just the derivative of the activation function. Is everything clear?
I'm sorry, but reservoir is something like derived from.
Yes, it's a special kind of neural network. And I think the main difference of the reservoir computing is that we only train the output matrix, as you can observe from the process. We initialize the W in, the H matrix, and we evolve the reservoir nodes without updating these weights. We only train the output matrix. Then, so now we know how to estimate the partial derivatives. Then from here we can construct the final link scores. So by the way, the idea of this partial derivative is just like the sensitivity of xi to the changes in the node xj. But this is just a partial derivative in a particular time point. So we want to make sure that the behavior of the partial derivative is consistent throughout time. So we basically average this all the values throughout time. And if this score is close to 0, then we can say that there is no link from xj to xi. But if it's very far from 0, then we can say that there is a link from xj to xi. So that is basically the machine learning part. Do we have any question?
What if the value is significantly changed according to the time?
Actually, I think that is one limitation of this paper. They simply average over time and they hope that the score is consistent throughout time. But anyway, they assess the performance later on and we can check. So yeah, that is the machine learning part. And now, as I mentioned earlier, there will be a part where we discuss some significance testing of the score. Sometimes even if we get a score from the inference technique, these scores may have occurred by chance. So this is a simulation of the scores from a system of 2 variables that I just tested. And as you can see, the scores from one node to the other are very different for these 2 cases. But actually, I simulated the scores using only using the same system. This is the underlying system here. But the difference is that for the first one, I used very fine sampling, and for the second one, I reduced the sampling. So you can see that in the first one, the scores are better because here we can see that x2 affects x1, and we can see that in this heat map. However, in the second case, the score for x2 to x1 is almost 0, so it wasn't able to detect the proper score. So in these cases where the results of the inference methods may have occurred by chance, what we usually do is perform some surrogate data testing. So this is just a summary again of how an inference method works. So after performing an inference method, we get some score, but we want to test how significant it is. And what are the chances of it occurring by chance. So for example, we have again x and y, and x, we consider x to be the causal variable and y to be the target variable. This is the original time series data for x, and what we usually do is just shuffle this causal variable multiple times. So we are just like interchanging the time labels so that we have this rearranged shuffled data for x. And for each shuffled data, we pair it with the original target variable and then perform inference. So that we have, for example, if we shuffle the data 50 times, we have 50 scores from the shuffled data. And then what we do is we build a distribution from all the shuffled scores. And after building that distribution, we want to compare the score from the unshuffled data to this distribution. So there will be actually two cases that will happen. First, here we have the gray boxes representing the distribution of the shuffled scores, and this is the score from the unshuffled data. So this is just this original x plus the original y, and if the p-value is significantly less than the rest of the scores in the shuffled data, then we can say that the score should not have occurred by chance. That is the first case, but the second case is that this is the distribution of the shuffled scores, and the score from the unshuffled data is very close to this distribution. Then we can say that the first case may not have occurred by chance, but the second case, it just occurred randomly.
Is this method is similar the method used in copy?
Yes, this is exactly what we do in Kobe to remove the false positives. So if this is the case where the score of the unshuffled data is very close to the rest of the scores of the shuffled data, we reject it. So the idea behind creating surrogate data is we want to create the score distribution for the case where there is no relationship between the variables. And if it's very similar to our actual score, then that means that this score should be rejected. But there is a problem with this method. So if you look at the shuffled data, actually it looks like just white noise, right? So actually if you pair the original data with the target data and the shuffled data with the original target data, then what are the chances of this relationship being significant compared to this? I think it will be very, very large because look at this, they look very synchronized, right? So it seems that they are affecting each other, but this is just white noise, and then you pair it with this data which has a pattern, then immediately you can see that, oh, this might not be affecting this. So sometimes you might just get a link just because they look synchronized. So essentially, in this random shuffling, this is the most common way of producing surrogate data. We are basically testing if there is a temporal structure, but we don't know what kind. And also, if we just randomly shuffle our data, it destroys all temporal structure, like your autocorrelation, the trends, and the periodicity in the data. So what we need is a type of surrogate data method that preserves some of the important temporal dependencies. And in this paper, they used what they call the amplitude-adjusted Fourier transform surrogate data method, which is a better method than just random shuffling. And so I will describe the steps of this AAFT method. The first step is to Gaussianize the original time series. So from the original time series, we just want to make a Gaussian version. It's very simple. First, we just generate a random Gaussian time series. And then we rank both the original time series and the random Gaussian time series. And okay, I think this is very understandable. We just arrange them according to increasing value, and we match their ranks so that the highest value in the original time series, the highest value here will be mapped to the location of the time series in the original time series. Basically, we're just adjusting the amplitude of the original time series to match this generated Gaussian time series. That's the first step. And after Gaussianizing the time series, we perform the Fourier transform to this Gaussianized time series. And here we take note that the Fourier transform of the time series has two components, the magnitude and its phase. And basically what we do with Fourier transform is transform the time series from the time domain to the frequency domain. So that we have this kind of graph. This basically means that at this frequency, there is a very strong oscillation. And the way that we disrupt the data is by what we call phase randomization. So, as I mentioned earlier, for each k here, there is a particular phase. So phase is just the location of the wave on the circle at a particular time. So if we randomize the phase, because it also corresponds to a particular time point, then that means that we are also disrupting the temporal structure. But in the way that we change the phase instead of simply just interchanging the time labels. So, simply speaking, in these two components, we are just changing this part. So that if we check the frequency versus magnitude graph of the randomized one, it is the same as the original Fourier transform. So basically, we randomize the phase, but we preserve the frequency information. And the next step is that with the randomized phase, but with the frequency information kept, we perform the inverse Fourier transform. So from the frequency domain, we just put it back to the time domain so that we have this kind of time series data. But then again, the amplitude here is still in Gaussian form. So finally, as you can expect, the last step is just to match the amplitude with the original time series. So we have the inverse Fourier transform and the original time series. We rank them again and we match rank so that the inverse Fourier transform will match the amplitude of the original time series. And this is the final surrogate data. Okay, so now let's compare the random shuffling with the surrogates from the AAFT. As you can see, the random shuffling will produce this type of randomized data. Again, I said that it just looks like white noise. However, if you look at the surrogates from the AAFT method, it preserves some of the temporal data. So you can see that some of the oscillating behavior is still preserved in this randomized data.
Right.
Yes.
Do we have any good reason to Gaussianize?
I also asked why, but I think the very vague answer is that the Gaussian distribution behaves very well for the Fourier transform because the Fourier transform of the Gaussian distribution is also Gaussian. But if you directly apply the Fourier transform without Gaussianizing, I think it will give you very strange behavior when you make the transform and get the inverse. What they said is like, if your data is not Gaussian, maybe skewed, and then you perform the Fourier transform, it might change the distribution of the data. Okay. Okay, and now you can see here that the AAFT surrogates preserve the power spectrum. This is just frequency versus power. So for each frequency, we can see the amount of power contained. And if you compare the original and the AAFT, they look very similar. However, for the random shuffling, the behavior is not quite close to the original power spectrum. And it is the same observation with the autocorrelation plots. So this is the autocorrelation plot for the original data and the AAFT surrogates. However, if we take a look at the autocorrelation plot of the random shuffle, it looks very different from that of the original. So the autocorrelation is at least preserved with the better surrogate data method. So that is the process of the AAFT surrogate data method. Now we're gonna proceed to the applications. Is everything okay? Okay, so they applied the machine learning method together with the surrogate data method to the C elegans data. So this is just a type of worm, and they measured the behavior within each of the neurons that they measured within the worm. These are just some representative measurements in each of the neurons, and this is the underlying network for 8 neurons in the system. So this is like the ground truth. And they also applied it to the 8-node Lorentz oscillator network. So this is the underlying equations. And what they did to mimic the network of the C. elegans neurons is that they coupled this set of equations so that it will imitate these connections. So that using these representative simulations from this system, the resulting network should be the same as the one as the C. elegans network. So each of the nodes here is represented by one node in the oscillator network. Okay, and now I will define some terms that were used in the paper. For example, these are the simulated data, and this is the underlying network. So here, the red arrows correspond to actual links within the network, and the blue lines correspond to non-links. So that just means that in this case, there is no effect from Zi to Xi. And using the simulated data with very low noise and fine sampling and increased sampling points, they computed the reservoir scores of the non-linked and the linked scores. And they call this the ideal case because the parameters they use are good in this sense. And you can see that the linked scores and the non-linked scores is almost perfectly separated. So all of the linked scores have high reservoir scores, and all of the non-linked scores are almost close to 0. Then, okay, so this is the basis ideal case. And what they did is just change the parameters in the simulation. So for the first one, they simply increased the sampling interval to produce this simulation. So the first one is the ideal case. Second one, they increase the sampling interval, and for the third one, you can notice that it is almost not so similar to the first ideal case. So that when they took a look at the distribution of the linked and the non-linked scores, this is the ideal case, but as you increase the sampling interval, you can see that the gap between the non-linked scores and the linked scores is severely reduced. So this is what we want. But when we increase it, some of the linked scores are in the similar distribution as the non-linked scores, and it becomes progressively worse as the delta t is also increasing. We'll take a look at the surrogate scores later, and yeah. And similarly, even if the sampling interval is fixed at a very ideal value, if the data is truncated, meaning that the time points are reduced, then the performance is still bad. So again, in the first case, there is no clear separation between the linked scores and the non-linked scores, but as you increase the number of time points, this gap increases. Yeah, so this is expected because the time duration is just increasing. And they also vary the observational noise. So for sigma equals 0.1 and sigma equals 1, at least, the behavior of the time series looks similar, but if they increase it to sigma equals 10, then the time series is almost unrecognizable. So that if we look at the distributions of the linked scores and the non-linked scores, the first two are okay, but the last one, the performance severely decreased. Okay, but one surprising thing for me is that when they tested only the sub-networks within the network, the performance is still okay. So what I mean is that we have 8 nodes in the network. What they did is, in the first case, they only sampled the 4 nodes, which has only 5 links. And in the second case, they sampled only 6 nodes with 16 links and compared it with the full node network. And even in the case of partial node sampling, the separation between the linked scores and the non-linked scores are still very clear. So yeah, so most of the results are actually expected, I think, but except for this one. And finally, we take a look at the scores of the surrogate data. These are the green curves. So if you take a look at the scores from the surrogate data, they mimic the scores of the non-linked scores. So the surrogate data scores is a very good estimate for the case when there are no links happening. So that we can perform the surrogate data testing that I mentioned before. For example, here, this is your surrogate data, and if you test the actual score from your unshuffled data, and if the score is here, maybe denoted by the red lines, then you can say that there is a link. However, we can only do the surrogate data testing if the data is good. Because in other cases, here for example, this is the distribution of the surrogate data, but a large portion of the link scores are also located where the most of the surrogate data scores are located. So the surrogate data testing is a good way to reject the false positives, but it is only effective if we have a very good quality of data. So yeah, some take-home messages. Very basic one, the results of our inference method is only as good as our data. And the main idea behind the inference method here is that we can estimate the effect between 2 nodes by estimating the partial derivatives. And in case of the surrogate data testing, AAFT is much better than random shuffling, and it is very effective in determining a true causal link only if the data is good enough. So that ends my presentation. If you have any questions, please, you are very welcome. estimator of the data.
So if the link score distribution have some bimodal
Ah,
distribution, then
but not. Hmm. It seems like if there is a good separation between the link scores and the non-link scores, it seems like it is representative of the how good the time series you have is.
yeah.
I'm not sure if there are some like other factors that will affect it, but like by the basic foundation of it, I think yes.
But I think when we have some connection weights between the nodes,
Ah,
then yeah, then the link score might not have a bimodal distribution or multimodal distribution. That's possible. Could be possible.
maybe yeah.
In which point reservoir computing is used?
So the reservoir computing is used to first the main role of that is to estimate the output layer. And the weights in the output layer, they are used in the estimation of the partial derivatives. So actually, if you notice in this process, sorry, much. The main role of the reservoir network is to give us the W out. So we actually don't use the future states, but here we estimate the future states, but the main goal actually is to get the values of the output matrix because it is the one that we will use in the estimation of the partial derivatives here so that we can compute this score.
What if we just use the multi-layer function? We cannot do this.
I think it is still possible. I think the only reason they use the reservoir computer is because it is easier and faster. Because you save on training time because the only thing you train is the output layer. However, in the other cases of neural networks, you have to train also the weights within the hidden layers. So maybe
I think if we use the multi-layer neural network, then I think the calculation of Sij metrics in Sij. Yeah, it's difficult. So in the previous slide, you showed the equation, the calculation sheet.
yeah, it should be difficult because this also changes. However, in the reservoir computing, this is fixed, this is also fixed.
So difficult or impossible?
It's impossible. No, the calculation of H. How can we calculate the H matrix, ED matrix?
So do you think this is better than B?
I don't know if they are comparable because again, the foundation of this is just determining if there is a link. But in Gobi, we determine if the link is positive or negative. So, not sure, but actually, when I looked at the foundation, the basic assumption, it's very similar to Gobi, right? right? So the basic assumption of Gobi is also that the dynamics of the whole system is governed by the general OBE system. But not sure. But I think it will be easy to compare. But I will not do it.
Your intern project.
Possibly.
Well, Tony is not slave.
Are there other questions?
If we Gaussianize the data, the copy results will not be affected, right?
No, I don't think so. I mean, I don't think there will be a difference between Gaussianizing here and Gaussianizing in Gobi because we always start with just the time series. Oh, what if you should?
No, I mean, if you use raw time series to copy or Gaussianized time series to copy.
Well, in the surrogate data method here, we don't simply Gaussianize the data. We also perform all the Fourier transform.
Yeah.
So just to keep the characteristics of the original data.
I mean, not only for the surrogate, but just for the data you want to test. And so there will be some data times you want to test.
Yeah.
You will put then onto the copy.
Uh-huh.
And previously you just put the raw data. But
Yeah.
if you Gaussianize the data and then to copy.
I don't think it will really affect it because we are just, I think the basic idea of Gaussianizing is just we are reducing the amplitude, I think. Because if you take a look at the behavior, it is very similar. This is the original time series, this is the Gaussianized one. And in Gobi, actually, you're just looking at where the time series increases or decreases. So if you look at if you compare the original time series and this one, the parts where it increases and it decreases are the same. So it won't really affect the score from Gobi. Any other questions? Then let's wrap